How does a simple steel bar transform into a gigantic 500-meter chain? The answer lies in a symphony of fire, pressure, and engineering on a colossal scale. They are the vital connection for billion-dollar cargoes and the guardians for thousands of lives on the world's largest ships. A single faulty link, and the consequences are catastrophic. Let's dive in and find out how these monstrous chains are made. To shape something of colossal proportions, it all starts with the right raw material. These are solid bars of a high-quality, resistant steel alloy, the basis for creating one of the most durable elements in the shipbuilding industry. Using a bridge crane, operators transport the heavy bars to the start of the production line. The first phase is cutting. The bars are fed into an automatic bandsaw, programmed to cut them into segments of an exact length. The saw blade cuts through the dense steel with a cold cut. These ingots have just the right material to become links, the piece that, when joined with others, forms the final chain. Each unit weighs over 100 kilograms and is 5 inches thick. Once cut, the ingots are grouped and stored ready for the next stage. Hundreds of ingots wait their turn to enter an induction furnace. The heat will allow the pieces to be molded easily. From this point on, the process becomes a choreography of heat and force. One by one, the ingots pass through the induction furnace, where a magnetic field heats them from their core. In seconds, they reach 1,600 degrees Fahrenheit, becoming malleable and glowing red-hot. The ingot enters the press. The jaws hold it in place, the mold preforms it, and an arm bends it into a precise J shape. Now comes the crucial moment of joining it to the chain. An operator, using long tongs, inserts the U-shaped link through the last finished link. Then, with precision, he places it in the next station of the press. A horizontal press, with a force of hundreds of tons, pushes the two ends of the U against each other, forging a closed loop. The link is closed, but the joint is not yet permanent. To transform these two sides into a single piece of indivisible steel, the giant ring, still red-hot, is moved to the welding machine. Two copper electrodes hold both sides of the joint firmly in place. An intense electric current is applied. The resistance of the steel to the passage of electricity generates extreme heat that melts the metal at the contact points. This process, called resistance butt welding, creates a molecular fusion, ensuring that the link is as strong at the joint as it is anywhere else. The welding has been a success. The link, now a single solid piece, is removed. The intense shine in the joint area reveals the extreme heat to which it has been subjected. But the welding process has left behind excess solidified material, known as burr. To remove it, the link is placed in a final press. Hardened steel jaws hold it precisely in place, while other surfaces push with enormous force against the newly welded joint. In seconds, the burr is sheared off cleanly and precisely. The result is a link with a smooth, uniform surface, ready to withstand the most extreme loads. The process will start again for the next link. Simultaneously with the creation of the links, a parallel and equally crucial process takes place: the manufacture of the stud, the sole of each link. It is a solid bar fixed in the center, which acts as an internal support. It prevents the link from bending or deforming and multiplies its resistance. These pieces are the raw material for the studs. The segments are collected and loaded onto another production line. Their destination, like the links, is the furnace. This is the stud forging machine. The steel pieces come out of the furnace red hot, and an operator, with the help of tongs, places them inside the press. A special mold gives them their characteristic shape. The process is fast and continuous. While one piece is being forged, the next one has already come out of the furnace and is waiting its turn. Hundreds of studs are produced every hour. The newly forged studs, still hot, are collected in large containers. Back on the main line, the link, already welded and shaped, is positioned in a vertical press. It still retains the heat from the forge, a key factor for the next step. An operator inserts a cold hammer into the center of the hot link. The temperature difference is crucial. Two powerful side presses are activated, pressing the sides of the link against the ends of the stud. As it cools, the link will contract, trapping the stud with a force of thousands of tons. As an additional safety measure, a qualified welder applies a weld bead to the joint between the stud and the link. This ensures that there is no movement whatsoever, even under the most extreme conditions. But the chain is not finished. It still lacks a fundamental part: the bow shackle, the piece that connects the chain to the anchor. More demanding than a link designed to withstand more pressure and secure the system that keeps the giants of the sea in place. The process begins with a block of carbon steel, chosen for its high strength and toughness. An industrial saw slowly cuts it into sections. The cut takes 15 minutes to complete. The result is a 265-pound ingot that will be turned into a single shackle. Although this steel is very strong, it rusts easily, a detail that will be corrected later. After hours in the furnace, a special vehicle extracts the ingot. The incandescent color indicates that it has exceeded 2,200 degrees Fahrenheit and is ready for the press. The ingot is then placed under a forging press. With a force of 6,000 tons, the first blows begin to compact the metal, modifying its internal structure and improving its mechanical properties. A manipulator arm holds the piece while the forge continues to strike it to create the wider ends that will later become the shackle ears. The preform is now visible, with a narrower central body and two widened ends. The steel has achieved its preliminary shape, but for the final molding, it must be reheated in a furnace for hours. Meanwhile, the next phase is prepared, the installation of the final forging mold, designed and produced in the same factory. This work depends largely on the manual dexterity of the operators, who can take up to 3 hours to complete it. Using enormous wrenches, they tighten the anchor bolts to secure this heavy block of steel. Now, a critical step. To avoid thermal shock that could damage the mold, it must be preheated. The operators place pieces of burning steel directly on top of it. These sacrificial blocks transfer their heat to the mold, preparing it to receive the main piece. Simultaneously, the shackle preform, already heated above its optimum temperature, is removed from the furnace and carefully transferred to a forklift. A team of several coordinated operators springs into action. Using long levers, they guide the heavy piece toward a bending machine. A central piston holds it in place, while two hydraulic arms slowly bend it, giving it its characteristic arch or lyre shape. The arch is now formed, but it does not yet have its final shape. Quickly, before it cools, a forklift truck transports it to the final press. Just before stamping, the oxide scale is cleaned with a jet of pressurized liquid to ensure the highest quality finish for the piece. The press descends, and its immense force forces the red-hot steel to fill every cavity, defining the final shape of the shackle body with millimeter precision. Excess metal is squeezed out at the edges, forming burrs. In a final step, a die press cuts off these burrs, freeing the shackle body. The piece is removed, revealing a perfectly shaped form. Placed in a basket, the shackle body is forged. Now, the pieces that will complete it must be created. The most important element is the shackle pin. This component, which will bear the load of the entire assembly, begins its life as a 130-pound ingot. The heads of the ingots are placed in powerful electric heating furnaces to reach forging temperature. Once this temperature is reached, they are removed, ready to be molded by pressure. The incandescent ingot is placed vertically at the base of a press. An operator uses a tool to scrape off the scale, a layer of oxide that forms on the surface. A hexagonal-shaped upper mold strikes the end of the ingot, forging the shackle pin's head with a single powerful compression. The operators pick it up with tongs and let it cool. The manufacturer's mark and steel grade are stamped into the head by the pressure of the forge, a permanent seal of quality. The first forging blow has created the hexagonal shape, but it has also left a ring of excess metal at the base of the head. The pin is placed in a stamping press, which, with a sharp, precise blow, cuts off the excess metal ring, revealing the clean, final hexagonal shape. This die cutting phase is essential to ensure that the head has the exact dimensions and can be operated correctly with tools. With the pin now cool and solid, an operator uses a drill to create a small notch in the center of its end. This will serve as an anchor point for the numerically controlled lathe. In this stage, the rough surfaces are machined down to an exact diameter. The thread is then cut for a tight fit without slack. To achieve its final strength, the pin needs to undergo a 3-stage heat treatment. First, it is heated in a vertical furnace to over 1,500 degrees Fahrenheit to transform the internal structure of the steel into austenite. This state distributes carbon, the key ingredient in hardness, perfectly evenly throughout the steel. Next comes quenching, where it is cooled in an oil specially designed for this process. This shock fixes the steel into a new ultra-resistant form called martensite. The oil, unlike water, ensures that the cooling is intense, but not so extreme as to crack the metal. The result is a hard but brittle steel. That is why a final process is crucial: tempering. This involves baking at a lower temperature, around 400 degrees Fahrenheit, to eliminate that brittleness and transform it into toughness. And to secure this pin, its counterpart is needed: a nut of equally massive proportions, whose creation is a process of high-precision forging and machining. The process begins with a solid steel ingot. After being heated in a furnace until red hot, an operator transports it to the first forging station. While the nuts are forged with millimeter precision, it is easy to forget the extreme environment for which they are made. If they loosen or become slightly misaligned, the shackle will fail, the anchor will come loose, and human lives, ships, and millions of dollars in cargo will be endangered. This is the outer shape that the nut will have. The next step is to create the center hole. A punch descends with immense force, piercing the center of the piece and ejecting the excess metal core from the bottom. Once cooled, the forged nut moves on to the machining stage. A cutting tool first machines the faces to give them a smooth finish, and then an internal threading tool carves the thread with micrometric precision. This thread must be perfect to match that of the pin. Attention returns to the main body of the shackle. The ear hole must have the exact diameter and a perfectly smooth surface to ensure that the pin fits without the slightest slack, ensuring even load distribution. Next, an operator uses an angle grinder to remove any remaining imperfections or burrs from the forging, ensuring a smooth finish that is safe to the touch. Now, the shackle must acquire its final mechanical properties. Several pieces are placed on a support, The three-phase process of heating, quenching, and tempering is the same as we have already seen with the shackle pin. As it undergoes its transformation by fire, it is worth understanding the magnitude of the system of which it will form a part. Because this piece is not just a shackle, it is the connecting point for a colossal anchor chain. These chains are manufactured in 90-foot sections, a standard measurement in the naval industry known as a shot. The value of each of these sections can reach $7,500. Considering that a single giant cargo ship can require up to 1,600 feet of chain, the total cost of its anchor system can easily exceed $100,000. All that responsibility rests on this single piece, a steel that, after tempering, is as hard as glass, but dangerously brittle. That is why its transformation is not yet complete. The pieces are placed in a second furnace for several hours to reduce the fragility of the steel, giving the shackle the ideal combination of hardness and toughness. Immediately afterwards, they undergo a magnetic particle inspection, a process that uses magnetic fields to reveal cracks invisible to the human eye. The test is passed, but one last threat remains: corrosion. Salt water is relentless, and even the most resistant steel would rust within months without protection. To protect them, each shackle is immersed in a bath of molten zinc. The contents of this bath alone are valued at $100,000. At over 800 degrees Fahrenheit, the zinc bonds with the steel, forming a resistant silvery coating. This is hot dip galvanizing. In this area, the air can become charged with acid gases, so wearing a mask is essential for safety. In the harsh marine environment, this protective difference means decades of service instead of years. Finally, a last dip in a passivating solution seals and protects the zinc layer. Now the shackle body is finished, precision machined, hardened to perfection, and protected from the elements. For threaded parts, such as nuts and pins, standard galvanizing does not work, as the zinc would clog the threads. Therefore, they are spun at high speed after immersion, which removes excess zinc and leaves a clean protective coating. In the case of nuts, a heavy lid is closed to contain the violent spinning and ensure that the process remains safe for both workers and facilities. Certified, tested, and coated with armor, the parts are finally joined together to form a single enormous shackle. To prevent the shackle pin nut from loosening due to the vibration of the ship, a secondary lock is used. A safety pin passes through the central pin just behind the nut, creating a barrier that prevents it from coming out of place. One by one, they are placed inside large wooden boxes, prepared with a coating to protect the finish during transport. This is oiled paper that creates a barrier against moisture and prevents rust formation, ensuring that the parts arrive at their destination in perfect condition, packaged and ready for their journey. This piece of steel is a critical connection point on which ships weighing thousands of tons will depend on the vastness of the ocean. And while the shackles finish their journey and prepare for shipment, we return to the anchor chain. Its process does not end with forging. Now it must pass the most demanding tests, such as a magnetic particle inspection to detect any possible surface defects. The next test is fluorescent magnetic particle inspection. This method is more sensitive than the previous one. Although many factories use only one technique, here both are applied to ensure that nothing is overlooked. The sections of the anchor chain are transferred to a continuous vertical furnace, where controlled heating and cooling harden and temper the steel. Now comes the acid test. The chain is installed in a colossal tensile testing machine capable of applying a force of up to 24 megajoules, the equivalent of more than 2,400 tons. From a control booth, a technician supervises the load test. The machine stretches the chains to a predefined tension, well above their usual working load. Each link, each weld, must withstand this extreme force without permanent deformation. Once the test is passed, the chain is laid out on the factory floor. Now, a team of operators meticulously goes over each link with angle grinders, removing any surface imperfections and ensuring a perfect finish. The next step is shot blasting. The chain is placed in a chamber where thousands of small steel balls are fired at high speed against its surface. This process removes all rust and scale from the heat treatment, leaving the steel completely clean. With the chain now clean, the final protection is applied. This is a 10-meter deep pool filled with water-based asphalt. It represents a modern evolution in marine protection, offering a more environmentally friendly alternative by reducing harmful emissions during application. Unlike older solvent-based paints, it uses water as a vehicle, making the process safer for both workers and the environment. The coating remains flexible in cold, turbulent seas, preventing cracks and ensuring long-term durability. By completely encapsulating each link through immersion, maintenance requirements are reduced and it is easier to inspect for potential weak spots. Manufacturing anchor chains is expensive. Depending on size and quality, they cost between $750 and $1,300 per ton. This section alone, weighing 4.58 tons, exceeds $5,000 even before it leaves the factory. Now the chains must undergo the most rigorous scrutiny in the world. Inspectors from the leading maritime authorities in the United States, Norway, Japan, and the United Kingdom arrive to examine every weld, coating, and link. They are the guardians of global shipping, and their standards leave no room for error. In the factory's testing lab, small samples cut from the anchor chains are mounted on a tensile testing machine. This test shows whether the steel can withstand the brutal forces of the open sea. The impact test is the final hurdle. Small samples of steel are struck with a heavy pendulum to measure how much energy they absorb before breaking. This reveals the steel's ability to withstand sudden shocks without cracking. For complete traceability, each section of the chain is permanently marked. An operator stamps a unique serial number on one of the links. Finally, the chain, having passed all tests and quality controls, is ready. A crane lifts it and prepares it for loading. The heavy load is carefully placed into a container. This marks the end of an extraordinary journey. That of a simple steel bar transformed by fire and force into a product of maximum reliability, ready for action. From the factory, they are transported to the port and loaded onto giant global trade ships. Each ship is equipped with 1,600 feet of chain and an anchor. The anchoring system bears an enormous responsibility, as modern mega-container ships can carry between 200,000 and 240,000 tons of gross cargo. The value depends on the type of cargo, but on routes carrying technology, manufactured goods, and high-value products, it can exceed $1 trillion. Added to all this merchandise is the safety of the ship itself and its crew, who, in calm waters or rough seas, depend on their anchorage point. Without their chains and anchors, trade would come to a halt, and navigation would be impossible. Now their strength will not be measured in factory tests, but in sea storms during crossings between continents. And when they are needed most, they will perform as they were designed, without fail.